Good morning, everyone. My name is Kelly Kane, and I'm the Marketing Manager for EandM. Thank you for attending our Bill Hintz 10 Rules of Diagnostics webinar today. After the webinar this morning, we will be doing a short Q&A. Please type any questions or comments into the Q&A box, the chat box, or email us at eandmwebinar@eandm.com. Now I'd like to introduce your presenter for today's webinar, Bill Hintz. Bill has been working with Siemens Automation Products for 25 years and has many years of hands-on experience analyzing and identifying system failures. Bill is currently an EandM Siemens product specialist working with customers to design new applications for Siemens products. Good morning, Bill.
Good morning, Kelly, and thanks for the intro. And thanks everyone for coming on board with our diagnostics webinar. This diagnostics webinar, this is the second time we've done this, and actually we've incorporated a lot of the suggestions that came in after the first one. Diagnostics is an interesting topic. We've been doing this for a long time at EandM, a lot of machine startups and field service down situations and that kind of thing. And what we decided to do is come up with 10 rules that kind of made sense on how to approach diagnostic problems and how we might be able to kind of spread the word out and get some feedback back about other ideas on how to do that. So this is the culmination of that, and so let's go ahead and get started on diagnostics, 10 rules. The first rule is don't panic. Down situations and where machines are broken and production lines are down are a very stressful time for a lot of people. You can walk into a plant and see a machine down situation and a lot of people standing around with the lines down. We've got some unused labor. We've got production managers looking very nervous, and you can walk into a situation like that and quite easily be taken up with the emotion of the moment. So our recommendation is don't panic. Get involved and take the proper steps that you would take in any situation, and that's going. If you can keep your head while all those around you are losing theirs, then you're going to have a shot at being able to be a successful troubleshooter. Along those lines, don't panic. If it worked before, it can work again. Here's a picture of, boy, if we walk into this one, we might be a little questioning that rule, but over time, machinery in certain plants can actually see a long parade of different undocumented repairs and added functionality and Band-Aids, and you can end up with something that looks like this. And oftentimes you start wondering, does it make sense to try to yet again fix this, or do we just kind of start over again? And that's something, a suggestion can be made after we've maybe got them limping along again to say, hey, maybe I'm sure you've seen problems before with this, so you might want to take a look at maybe starting anew. Okay, second rule. Do no harm. This comes out of the Hippocratic Oath, the oath that doctors take. What we really mean by this, along the lines of diagnostics, is that we don't want to make the situation any worse than it is. Fixing a single fault is far easier than trying to fix a fault that someone else has tried to fix and done more damage to. So in other words, what we recommend here is just don't do anything you can't undo. If you're working on a PLC or something and you want to go in there and you think you need to change something or revert back to a prior program level, upload the software first, save it. Then go and do any changes you want to do. Just make sure you have a path back to where you were. So if anything that you think might have been the problem and you try to fix does not solve the problem, let's not leave that last fix in there. Let's pull back to where we were before and then look for something else. Also, document anything that you change before you change it. So in other words, oftentimes you'll get into a situation where you change something, you see something else at the same time, and you jump over and start changing a bunch of things, and then, boy, what was that first thing I changed? So if you can document every step you take along a diagnostic repair procedure, then Everything from wiring changes, part replacements, any change that you make, just make sure you write it down, because in that situation you can oftentimes forget things that you did change. Another point here is if you're not sure why you're changing something, don't. Fixing by replacing things is really not a very good diagnostic tool. I've been in situations where people have replaced parts that are programmable or have some kind of configuration switches on them or something, and now you've got another problem on top of the original problem, and trying to diagnose two issues is much more difficult than just the original one. So fix by replace is really a poor diagnostic method. And if you're not sure what went wrong, then don't start trying to fix things. I mean, really, we're going to talk a little bit later about treating the cause, not the symptom. And I mean, for example, you can. I have been to a plant where they have said, you know what, that light bulb keeps going out on me, and I've changed it about 4 or 5 times now. Well, you know, you might want to consider maybe it's not the light bulb. I mean, maybe it's the wiring to the light bulb. Maybe it's something else. So let's not treat the symptoms here. Let's treat the cause. Make sense? Okay. Diagnostics rule number 3: get your ducks in a row. And what we mean by this is you need to have all your tools with you. Oftentimes when we're doing a down situation diagnostics trip, we're going to actually be driving a little ways, and if you don't have everything with you once you got there, then it makes a single diagnostic mission a lot more difficult. So if you don't have a screwdriver or a schematic or a manual or a laptop or any of these other things that you might need, I guess the basic rule is here, just make sure that anything you can think of, just throw it in your trunk. If you don't need it, that's fine. Bring it back home with you. But, I mean, the example that I've oftentimes thought of is I do a lot of work in clean rooms. And for those, you're actually doing the suiting up process, which is, you know, it's pretty time consuming. It's a pain, actually. And you take things into the clean room, and once you're in there, then if you've forgotten something, then you have to go through the whole process again, desuit, go out, find whatever tool you need, resuit back up and get back in there. And a lot of the time lost there, and it's just good practice to bring everything you can think of. Okay. Rule number 4, talk to the guys in the trenches. What does that mean? Essentially, perspectives can differ, and this can be kind of a tricky one because the guys in the trenches sometimes will actually, there's a little fear involved here. I mean, nobody wants to take the blame for something that went down and so forth, but typically what I've found over the years is that the guys in the trenches are the ones that have been working on these machines for much longer than even the people that design the machines, and oftentimes they know them and they have tribal knowledge built up, so that you know, ask them a few questions, see if it makes sense what they tell you. I mean, for example, what happened? Let's just hear it from their mouth. Did the machine ever run? And that, what we mean by that is if this is a startup, it's a whole different diagnostic game than if it's a machine down situation where this was a running machine that faulted out. First installs can have a whole slew of problems, and you never know until all the I/O's been wrung out and everything's been checked whether the machine's going to work or not. Typically, when we see a machine down situation, we're going to see at least a single root cause of a fault. The root cause may cause several faults in the machine afterwards. I mean, for example, if we had a power spike, it could take out a couple of different items on the machine. But typically, a down situation is something we can trace back as opposed to a first install, which is kind of a whole different situation. Ask them, has this ever happened before? And what did you do then to fix it? I mean, sometimes these are recurring problems that kind of will give us a lead into how can we get to the root cause of this problem? I mean, if there's been a continuous problem with a wiring issue that the wiring keeps breaking or something, maybe it's going through a flex process, and over time it just breaks the wire. So maybe a little bit of thought into how we might be able to improve the machine might make sense there. And here's the tricky one is what repairs have been made this time. And what this will kind of lead us into is if there's somebody that's afraid, and probably legitimately so, that, you know, they tried to do something and it broke the machine, it might be a little bit difficult for them to own up to that. And lastly, just ask them what do they think is the problem. Sometimes you'll get some misleading information, but you never know. Sometimes there have been kind of a decree that this is the issue with this machine and you will believe it, and sometimes the guys out on the floor have a different opinion. So it's worth taking into account all the different possibilities. Okay, let's talk about how we might localize problems. Oftentimes when we look at a large machine, it can be a bit overwhelming. I mean, the machine's down. Why is it? I mean, sometimes we go to a huge printing press that takes up an entire room, and it can't be everything broken at once. So if we can actually localize the problem down to maybe some subsystem that's actually starting the problem. So once again, talk to the people on the floor, and maybe it's a problem with for example, a temperature controller. This tank is going awry. So maybe we just focus on a temperature PID loop that's on a tank or something along those lines, so we can pretty much ignore everything else in the system for the most part and focus in on a localized problem. So what this means is kind of system problems versus local problems. System problems are actually going to be things like communications. We may have a Ethernet network or something along those lines around the machine. When system issues pop up, they can seem random and they can appear at various different parts of a machine. So noise issues can oftentimes be a communications issue, or they can actually, noise issues can find themselves getting onto analog signals and so forth. So we're actually seeing values coming in from a thermocouple, for example, that couldn't possibly be. And what it does is when the machine's control system sees a temperature jump up 100 degrees, maybe it shuts down. And those could be caused by noise, and it could be a wiring issue. It could be a wiring routing issue and those types of things. It could be loose wiring. Loose wiring is kind of gets us into the possibility of an intermittent fault, and we're going to talk about that in a minute. Non-system or local problems, kind of a device-level problem, can be fixed more easily than systemic problems. Typically, you can actually take it down and once again look at the individual sub-component of a machine and kind of just focus in on that and fix that, and you've probably gone a long way towards getting the machine back up. Okay, for diagnostics, if we can reproduce a problem, and what they're showing here, the keyboard, every time you hit that bug, the thing happens, boy, we can pretty much figure out how to fix that. That makes it quite a lot easier. So if you can make an issue happen over and over, you're well on your way to finding the cause. So in other words, shaking the wires actually creates the symptom every time, or if you actually see a sensor kind of misaligned and not hitting every time, and once you've get the sensor in the right spot, it actually you can actually figure from that hey, there's how we solve the problem. If we can't reproduce the problem, we may very well be in what we call intermittent land. And intermittent problems are the most diagnostically intense, shall we say, issues. They're fixable, but you actually need to sometimes it can take a lot more time, and sometimes it takes a little more investigation to try to figure out what an intermittent problem might be. When you're doing, number 7 here is when you're doing intermittent problems, you need to use some tools. And a check engine light is a good example of a tool on a car that actually, when that light comes on, it latches. So in other words, if there was a fault on your car somewhere that happened and that light comes on, if the fault goes away, so in other words it's an intermittent, then that light stays on. And the diagnostic guy is going to plug into your port in your car and try to figure out from that what the cause of the fault was. So these tools are invaluable with diagnostic, intermittent diagnostics. And if you've got that tool, then intermittence can be repeatable if you can find the cause. Makes sense. And oftentimes programming software and systemic software can give you things like diagnostic logs and fault tracing. And I've got an example of that I'm going to pull up for us here. Let me go ahead and pull up. This is the Siemens S7 TIA portal software. And what we're looking at here is the new controller. I've actually got the hardware running here. This is a 1500 controller, and it's hooked up to some remote I/O and a HMI station and a Ethernet switch. So if we were to actually go on to the diagnostics of this PLC, I can click over here on Online and Diagnostics. What it's going to do, I'll go online here, is tell me what's going on with our PLC at this point. And if I look over here, I see all these nice green dots, so everything looks fine. And if I were to look at diagnostic status, module is there, and it's okay. So right now we don't have a fault, but I can fix that. I can create a fault by, I'm going to go over and remove an I/O module. Bear with me for a moment. I'll be right back. So what I did is I actually pulled out an I/O module and then I put it back in again. And so now we're back to the original state we were in where the module exists and we're okay, but that kind of simulates what would happen on an intermittent fault. So at the graveyard shift, as is typical of machine faults, it happened, the machine went down, they power cycled it and everything came back up again, but nobody knows why. You can come in as a diagnostics person to try to figure out what happened, and if you just look at the machine all day and it's running fine, and I've done that, believe me, it's interesting because it never seems to fail that I'm driving back to the office halfway back, then I get the phone call, it happened again. So unless you can duplicate a problem, then you're going to have a hard time saying that you fixed it. So what Siemens gives us with the 1500 and most all of their PLCs is what's called the diagnostic buffer. So I can actually look into the buffer and it will actually tell me what's happened in that PLC and timestamp it. So we can see here on today at 10:16, I had a hardware component removed or missing, and that's pretty much what I did. Is I actually pulled out the module and put it back in again. If I look at help on event, it's going to say hardware component has been removed and or cannot be addressed and that kind of thing. It'll give you some possible causes. And actually the first one has been plugged in and can respond again. So yeah, that's exactly what I did. Let's see if there's anything else in here. If I go open an editor, what it's going to do is it's going to actually show me the I/O module that went out. So it looks like I pulled out the digital output module there. It's working now, but this is where we talk about using our tools, because a diagnostic fault that is intermittent is really tough to chase down unless you can repeat it. So now, if I want to repeat that, I just pulled it out again and left it out. Now we can actually see that when we're doing our diagnostics, if we can figure out what the fault was, then we can repeat it. And now we see that that's the fault. So maybe there's I mean, for example, I doubt somebody's pulling the module out in the middle of the night. Could happen. Maybe it's just loose in its socket. Who knows? But in this case, the diagnostic tools for intermittent faults are really invaluable. Okay. Let's go to rule number 8. This is an interesting one because it's not always the most complicated part that causes a down situation. interesting because it's most often blamed as the cause because, let's face it, a lot of times if it's a programmable controller or some high-end servo system or something like that and people don't really understand how it works, it's pretty much universal human nature to say that must be it. So it's not always the most complicated part, and in fact, it's almost never the most complicated part. It's actually something peripheral to that, especially if we're talking about PLCs. And the reason being, I mean, PLCs these days they have what's called an MTBF, or a mean time between failure, that's measured in decades. So the chances that the PLC itself went out, pretty slim, at least in comparison to some of the possibilities that some of the other issues would be causing the fault. So loose wiring, I/O modules, that kind of stuff is much more prevalent when we look at faults, because the PLC is typically sitting inside of a nice enclosure, usually with the door closed and temperature controlled or whatever. Not always, but usually. Where the rubber meets the road is actually through the I/O. So in other words, we can have I/O cards that are right there in the PLC rack, but the wiring goes outside into the real world, and that's where things like arc welders are going on and forklifts running over conduits and all that kind of stuff. So the I/O is much more likely to be faulting. Now, I/O cards have a very high mean time between failure as well. So as long as we keep them within what their standard operating limits are, so in other words, most of them are solid state. So as long as you keep the temperature down and you don't overcurrent an output, for example, those transistors on that output are going to last pretty much forever. If you run over the wiring with a forklift and dead short the output, that may not be true. So in other words, it's those faults, those hazard faults that actually create the problems, and typically they're not with the PLC itself, the CPU is what I'm talking about, but with its I/O, and that's much more likely to be causing the problem. Network noise, loose wiring symptoms, they often look unexplainable. So in other words, it could, people will say, the thing just went crazy. It has to be that crazy PLC. Or it always works while I'm watching. Well, intermittent, once again, can be a problematic diagnostic exercise. Networking issues oftentimes are caused by electrical noise and so forth, or just loose wiring once again. So the diagnostic log's invaluable. We can actually see if there's a network fault that's happening currently in the programming software I just showed you, we would actually see a red wire, and we'd know exactly where the problem was. If everything is green, once again, back in the diagnostic buffer, and it will tell you where to go look. Okay, and now we're kind of getting into the nitty-gritty of diagnostics, and one of the main things to think about here are root causes versus symptoms. And typically symptoms are what people treat, and this is it's the easiest thing to try to fix. I mean, certainly if you, like I said, if the light bulb's out, then you're going to go put a new light bulb in. But if it keeps going out because of a power spike or something along those lines, then that new light bulb's going to go out as well. So we need to dig a little deeper to find out what caused that problem and why it keeps happening. So if we can treat the cause and not the symptom can lead us to where the cause is, but it's not necessarily the cause itself. So once again, damaged loose wiring, the top of the list on culprits for when we're going to see problems that can be intermittent or can be just obvious. Sometimes one of the things, the feedback we got from our first diagnostic webinar was, just look at the machine. I mean, oftentimes it's really simple. I mean, there may be a plug just unplugged from a solenoid valve dangling under the machine, and that's all it was. And so just a good survey of the entire machine itself before you do anything else makes sense. You might find a puddle of hydraulic fluid underneath the machine. You never know. Anything like that is it's just a good start. Power. Power is an interesting one. Power failures and so forth can cause all kinds of problems with modern machinery. There's also new modern DC power supplies have a neat feature to them in that if you short them out, they turn off. And if you remove that short, they turn back on again. So oftentimes that can be once again, the intermittent problem we're searching for. So, and we have ways of fixing that. I mean, effectively, if you've got one 40-amp DC 24-volt power supply running the whole machine, there are components that we can actually add to that system to make it a lot more resistant to complete shutdown. So actually Siemens makes a nice little module that goes downstream of a big power supply and divides up that high current power supply into, let's say, 4 different 10-amp circuits so that we can actually isolate the individual circuits and not lose the whole machine. So somebody dead shorts a sensor on the far end of the machine, rather than shutting down the whole machine, it just shuts down that 10-amp segment that we've isolated out and keeps the PLC up and the HMI and all the diagnostic tools are still there. And that makes a lot of sense for kind of isolating out problematic areas. Part failure. We talked about I/O being most likely, and that's typically because it's been overcurrented or it's had a spike or temperature or those types of things. But let's get away from the electrical for a minute. Let's just talk about some of the simple stuff. I mean, sensor alignment. I spent a good half a day on a machine one time that we were just absolutely positive that there was a software bug because it was a new install. It had been running for about a week, but it kept having the same problem. And it was a pusher arm, and it was sticking out, and it wouldn't come back. And we go in there, and we would. Apparently the guys on the floor would shake it around a little bit and it would come back again, and couldn't figure out why. So we kind of scratched our heads over that one for a while, and finally we figured out that it was actually the sensor was not seeing the pusher at the end every time, and it was kind of passing by rather. So when it was fully extended, the sensor wasn't on. When it went by, it would flash, and occasionally that would work, or most of the time it would work. So and that kind of brings us up to another point, 2 down from that, from the sensor, is the pneumatic flows and cushion valves. I mean, that was really the problem there. The guy that had adjusted the sensor had done it at the extent of the cylinder, but cushion valves actually keep a pneumatic cylinder from slamming when it gets to the far end. So actually, when it gets down very close to the end, there's an air valve in there that actually slows things way down. So if you set your sensor so it catches it just before it gets to that end, it's going to go right by it. And cushion valves and flow valves, which are actually used on the far end of the cylinder to slow the speed of the cylinder itself, they tend to change over time, so they may get clogged up, air can get dirty and so forth, maybe a little bit of lubricant gets stuck in there, and so just basic machine adjustment sometimes is all that's needed to get rid of what seems to be a very persnickety little intermittent problem. Mechanical jams. Hey, sometimes it's just, you know, that push arm can't return all the way back because it's got a bunch of cardboard box pieces behind it or something, and that's typical of machinery. One of the things to think about with a machine, especially one that's been in the field for a long period of time, typically software doesn't change. So it may have a PLC in it, it may have a very complex program. But if it's been working for a long length of time, chances are pretty good you don't need to change the software. These electrical wiring issues, the mechanical jam issues, the cushion valves and sensors, and all those things are much more likely to be causing a problem. And lastly, if you can't point to what caused the problem, it's probably not fixed. It's too often we actually go out there and move things around a little bit, and it starts working again. You're not real sure what actually fixed it, and it started running, and it seems to be doing just fine. But boy, I'll tell you, those are the ones that are likely to come back and bite you, because unless you're pretty sure about what it was that caused the problem, it's probably not fixed. Okay. Lastly, and a lot of people commented on our first one that this last rule is probably the most important. Certainly, it makes long-term viability of a machine a lot easier and more possible. Essentially, if we will document what we do to a machine, we actually give the next guy in line a leg up on how to fix it if we're having a problem again. Or if it's a repeating problem, then we know about it. So it's something that we can fix on a machine, maybe some kind of a design change or something along those lines. But essentially everything, software, any changes that were made in software. I mentioned that most of the time software is not going to change. So, but oftentimes things will happen like it's amazing. The machine originally shipped with a disk, and things get changed over time. And it may not be the actual structure of the code, but it may just be recipe changes and those types of things. So, if you're changing anything in the code or the set points or any of those types of things, document it, and then the next guy's going to actually have a pretty good idea of where to go. Schematics. If there's a wiring change or sometimes sensors are not the same polarity and you have to change the wiring around a little bit. Document that, please. Redline a schematic, write it in the procedure logs of the machine and so forth. Any manuals that the machine have with it, mark them up, put a sticky on there, do something to actually let somebody know that you've been there before and this is where you found the issue. Procedure logs, or if customers don't have a procedure log, this is something that they should start, oftentimes called a maintenance log, and just everything that happens to a machine should actually be logged in there. And this is where I put suggestions as well. I see in the log here that this event has happened several different times. This is a suggestion for a fix so that we won't see that happen quite so much anymore. Okay, I've got a couple of other things I wanted to talk about here, but we're seeing some questions come in, one of which was the 1500 I was showing. Is that available? Yeah, actually that's the new kid on the block, so we're going to be doing actually a roadshow. I'll be teaching it in Northern California starting at the end of September, so go ahead and jump on my EandM or EandM.com. And you will actually be able to sign up there. We're doing 10 cities throughout California over 10 days. So hopefully there's one near you. You can sign up for that. And we're going to be actually using the 1500 and a comfort panel. We'll have a drive and doing all kinds of wild stuff. All right, so just kind of an overall of the 10 rules again. First of all, don't panic. If it worked before, you can probably make it work again. Second of all, do no harm. If you're going to go in there and change something, make sure you know why you're doing it and you can back yourself back out of it in case it doesn't work. Get your ducks in a row. Get all of your tools and everything kind of laid out and with you so that you're ready for anything. And talk to the guys in the trenches. They actually know a lot about those machines oftentimes. They've been working with them for years. Localize the problem is number 5. Don't look at a machine as this gigantic monstrosity and how can I possibly fix this. Machines are designed in subsystems. So typically if you've got a big machine, you're going to have an HMI system and you're going to have maybe a temperature controller and maybe a motion controller. And if the software was written well, then it actually is going to differentiate and have different structures for each one of those different subunits. But if you can focus in on what you think might be the cause rather than looking at the overall picture, things become a lot more clear. See if you can reproduce the problem. If you can reproduce it, you can probably fix it. At least you will be able to know what's causing it. And reproducing the problem is probably step 1. Once you've got that reproduced, as long as it's not an intermittent, you're probably going to be able to fix it. Number 7 is use your tools. So the diagnostic logs, the software will actually go a long ways towards showing where faults are and help you diagnose things. And also, if you're designing a machine, think about the guy that's going to be maintaining it. And a lot of the things that I showed today in diagnostic logs can be popped up onto an HMI screen locally, so you can actually have someone in the field being able to see that diagnostic log and be able to diagnose and fix intermittent problems or current problems as well. You can also you can pop up things like manuals and schematics in HMIs. It really, if you design for maintainability, you're actually creating a machine that's actually going to have a lot better uptime. And if you're a machine OEM, then you're probably going to sell more machines. Remember that it's not always the most complicated part, and that kind of goes along the lines of localizing the problem, but typically even within a subsystem, people tend to think, it's that crazy PLC thing. It's not the sensor. Especially if things are acting crazy, and what they can do with intermittent problems or just like a networking or a loose wiring, they can, sometimes it's a ghost in the machine. Boy, that just doesn't make any sense at all. But if you localize it, kind of look on just the small picture on what's happening there and be able to reproduce the problem, you should be able to get that fixed. And treat the cause, not the symptom. So you may have to fix some things that were broken by the cause. So in other words, we may have spikes and so forth that blew up an I/O module, or you may have a solenoid valve that dead shorted and actually took out the I/O module, but you need to replace everything and get it all back to where it was working in the first place. Lastly, document everything. I may be working on this next. I appreciate it. Certainly anybody that's coming in after you, and it may be you as well, and you can't remember exactly how you fixed it the last time, this is a time well spent. And also throw in the logs there any suggestions that you might have about how you might be able to improve the machine in the future so we don't end up with that big bundle of wires I showed in an earlier screen. Okay, that's pretty much what I've got for Diagnostics 10 Rules today. Once again, if you guys have suggestions, please send them back to us. I'd love to incorporate them in the next one we do. And look forward to seeing you on the roadshow. Thanks.
Great. Thank you, Bill. And if anyone would like to review a portion of this webinar, a recording will be available on our website, EandM.com, this afternoon. And also, like Bill said, if you have any questions or if you have any feedback, feel free to email us at EandMwebinar@EandM.com. And thank you, everyone, for attending, and have a great weekend.
Bye now.